Welcome again to this lecture, this little short course, which is going to be about information, black holes, and the holographic principle. So today is the first lecture, and it's going to be every Monday at this time. I'm going to tell you all kinds of sources that you might want to look at, like review papers and things like that, original papers. There's a number of books about the topics that I like. So there's obviously different levels of books. Like there's these books that are completely meant for the general public, like The Elegant Universe or A Brief History of Time. And then there's these advanced textbooks that are really meant for study and self-study. And concerning the holographic principle, there are books like the three that I put here on the bottom row. Gauge Gravity to Reality by Ammon and Erdmenger. I should say that this book is written by my PhD advisor and another good friend of mine, so I absolutely recommend it. Then there's this book by Nastase, which is a bit more, in my taste, more technical and more on the string theory side. And there's this ADS-CFT user guide. But these books are all very much on like research level. And they may be very advanced for some of the people here. As I said, the lecture itself tries to be more accessible, and there's a bunch of very nice books that are somewhat in an intermediate level, like the three ones that I have at the top here. And these are very nice books that I like a lot, and you can essentially read them during your vacation on the beach. That's the kind of level they are at. So you have The Nature of Space and Time by Hawking and Penrose that doesn't talk about holography, but it talks about black holes, thermodynamics, and stuff like that. And the chapters that Hawking wrote of that book are actually on the archive for free. So you find them in this literature folder here on Microsoft Teams. Another book that I like is this one by Susskind and Lindesay about the holographic universe. That's a book that I'm going to stick most closely to during this lecture. And then in general, for physics of all kinds, theoretical physics at least, The Road to Reality by Roger Penrose is something that I absolutely recommend. So those are just a few suggestions for people that are maybe interested in studying these topics beyond what I will be able to cover in these 15 hours of lecture. So, so we can start the first part of the lecture, which is going to be about the basics of information theory. Specifically, we're going to talk about Shannon entropy. So here you see this picture that I took in the math department here. In case you haven't seen it, they have this little veranda or terrace with these kind of all kinds of symbols and paintings and whatnot. And information theory is clearly a very modern and important topic, which you can see already from the fact that here at Jagiellonian University, both the physics and the math department decided to put the concept of information theory right in their names. And of course, they didn't do that just because of one or two papers. There's obviously a whole theory to this. But for our purposes, we are going to look mostly at two very, very important papers from that. And first, we start with this famous one by Claude Shannon called A Mathematical Theory of Communication. So suppose we want to transmit a message from A to B by encoding it and sending it via a transmission channel. And then it's received and decoded so someone else can read it. And there's different ways how we could do that. For example, we could simply write a letter in natural language and send it via ordinary mail. Or we could use radio and telegraph to transmit a message in Morse code. Or we could, for example, encrypt the message and send that via another channel, right, like radio or mail. And for simplicity here, we are going to focus exclusively on the noiseless discrete communication systems. Noiseless means that essentially the signal is received perfectly, and discrete means that the message and signal are essentially a sequence of discrete, perfectly distinguishable symbols, call them SI with an index I, chosen from a finite set of allowed symbols, which we call an alphabet. Okay, and So for simplicity, we will focus on a noiseless. Oh yeah, that's what I said. Sorry. I should also say, usually, of course, when I give a talk, let's say at a conference, I would never make slides that full of information. But for the lecture, well, there's obviously a lot of information that has to be conveyed. So I hope everybody can follow. But I'm going to try to be very, very slow and explain everything in detail. So a signal is a sequence of these symbols. And let's assume every symbol takes a time ti to transmit via the channel, and that time may vary from symbol to symbol. Furthermore, in principle, not all combinatorically possible sequences of symbols may be actually admissible signals. If you want to have an example for that kind of restriction, you can consider LaTeX, for example. These slides I wrote in LaTeX, and sometimes if you forget to close a curly bracket or so, then your code simply doesn't compile, and there's an error. So that's an example of a sequence of symbols that you typed, which would not be a loud signal, so to say, if you want to imagine the compiler or so as your transmission. So, and then the first important definition is the capacity C of the transmission channel is defined as this limit where n of t is the number of possible allowed signals of a length about t, and so the limit log of n of t over t, and the limit t goes to 0, that's the capacity. So we look at essentially infinitely long sequences and how many different sequences are there that we can transmit in this time t. That may be a bit technical, but let's look at an example here. Suppose we have an alphabet with n symbols, and for simplicity, assume it takes the same time to transmit all of them, namely 1 second. Ti equals 1 second. That means in a time capital T, we can transmit T over Ti symbols. For example, if capital T is 1 minute, that's 60 seconds. That means we can transmit 60 symbols. I'm writing about here because obviously if this was not an integer number, you might run into problems. But for the moment, just assume this is always an integer. And so there are n to the power of the number of symbols possible sequences. Essentially, if you can transmit so many symbols, that's like a number of slots. And for each slot, you can fill in one of the n letters. For the next slot, you can fill in one of the n letters. So in total, there are n to the power t over ti possible sequences of that length. And now assume additionally that all of these sequences are allowed signals. So there's no kind of restriction on that. That means that the number of messages of a length capital T is precisely that number. The number of symbols to the power of capital T over the time it takes to transmit one symbol. And then we can plug this in here in this formula, log of n to the power T over Ti. Of course, this is T over Ti times log n, so the capital T cancels, and we end up with log n over Ti in this limit, which we kind of don't need anymore. So let's look at an example. Suppose we have a binary channel, which means we have two symbols we can transmit, 0 or 1. Then n equals 2. The log of 2 equals 1. When I write log here, I mean to the base 2, so this is exactly 2. And we can transmit 1 bit per second. Sorry. And if instead of 2 letters in our alphabet, we have 2 to the m, then log of n equals m. And then we can transmit exactly m bits per second. I guess that kind of example makes this definition of the capacity understandable. Are there any questions about that so far? Okay. Having defined that, sorry. Yes. We should try not to get confused about the words here. So this is the capacity for information transmission. But depending on how you encode the actual information content you want to rely, the rate in which you can transmit information may be different. So consider the example of English as a natural language. And everybody who has like maybe studied code breaking and cryptography, or who has read about that for fun, will know that not all letters in English appear equally often. For example, here we see E is the most common letter in English, and then things like X and Z are less common. And that means that receiving a certain letter via a natural language may actually give you different amounts of information, so to say, depending on what letter that is. So let's consider the following example. Suppose you are solving a crossword puzzle, and your task is to guess the name of an ancient Persian king, which has 6 letters. Okay, maybe you don't know any. Let's suppose you find out that, okay, sorry. No, it's not. Oh, someone wrote in the chat, it's not Darius. Let's suppose you find out that the 4th letter is an X. X is a very, very rare letter. So that kind of gives you a lot of information, and maybe now you can guess what the name is. On the other hand, if you find out, if you would instead of that find out that the 5th letter is an E, you might think that gives you kind of less information because E is a much more common letter. So technically speaking, this graph here is only about the letter frequency in English, and of course that wouldn't technically apply to Persian kings, but of course their name Xerxes exactly. The solution is Xerxes. Of course, that technically doesn't apply to ancient Persian, but you know, when we write Xerxes in the Latin alphabet, that's kind of transcribed anyway. So to a certain degree, the X is more helpful here than the E. I hope that's a good example. So you can use that to try to encode a message in natural language more efficiently. And in fact, that's done already with Morse code, which was invented before the paper by Shannon. So this is a good example of, you know, people solving a problem already before it was mathematically well defined. If you look at Morse code, you see that the E, the most common letter, is given the shortest symbol. And then letters like T and A, which are like the 2nd and 3rd most common letter in English, they are given the next best short kind of sequence. On the other hand, very, very rare letters like X and Z are given longer sequences by comparison. Now you may notice that Y is given a comparably long sequence in the Morse code, despite being not that unlikely in English. I actually don't have an explanation for that. Maybe it's because Morse code is not exclusively optimized for English. Maybe it's because they just didn't employ this kind of philosophy 100% when defining the Morse code. What we, however, assume in this kind of table here is that, well, essentially every letter is chosen randomly and independently of the preceding one. That's not the case in natural languages. For example, you know, if you have a Q, then you know the next letter, because of that, is very likely a U and very unlikely a X or anything else. So there's kind of correlations between letters over so-called diagrams, trigrams, you know, groups of 2 letters, 3 letters, and so on. And this fundamental paper by Shannon actually explains a few very interesting statistical properties of the English language and how you might approximate it to various degrees of fidelity with statistical progresses. And also this very nice book about information theory by this French scientist that I'm not going to try to pronounce. also gives information about, statistical properties of the English language. So if that's kind of interesting for you, I absolutely recommend to look into that. So having said all that, we can now try to formalize this approach to information more, in which a rare event gives us more information than a very frequent event, so to say. But are there any questions so far for this? Well, I would say it's not as important, but it's the second most important thing, and then so on for the higher cases. So I actually have the Shannon paper open here. We can have a look at this more closely if you're interested. Let me see, where does he do this? Yeah, a series of approximations to English. The zero order approximation, is this big enough? Can everybody read it? The zero order approximation is one where you just pick symbols from the Latin alphabet, 26 letters and a space, a separate letter, and you give all of them the same probability. Obviously, that's just garbage text. And then the first order approximation, in which symbols are independent but with the frequencies of English text, still garbage. And then you can go to the second order approximation, where you have the same diagram structure as in English. So for example, QU and TH will be more common than some others. And the third order approximation, that already starts to give you some plausible short words, or at least things that look like they might be words. Demons, for example, here. And then instead of looking at the probability of letters, you can do a different approximation where you take words from the dictionary and you take them as your symbols. So each word is a symbol, and you look at which words are more common in the English language and not. And then, the first order word approximation is one where every word is a genuine word from the English language, but it appears at the frequency at which it appears in the English language, but each word being chosen independently. And then the second order word approximation is one where you take into account correlations between words. And if you look at this, it almost sounds like there might be some meaning behind it. At least some short sequences of words seem to make sense with respect to each other. So those are increasingly good approximations for English. And yeah, let me quickly look at this book by Briouat, because he said a little bit more about this. So this book is called Science and Information Theory. And he also has a little, he starts with the same things as Shannon. And he has, the redundancy in the English language, 21. Page 21. Oops. Yeah, the page 21 is in the PDF is not the same as in the text. So, okay. Redundancy in the English language. So he discusses this a bit. Obviously, I'm not going to tell you all the details here. I just want to show you one thing that comes later on here. Here he actually tries to estimate the redundancy in the English language in total. And like the statistical properties of letters and bigrams and trigrams are easy to look up. They were already known at Shannon's time. But if you want to know the statistical properties of, let's say, 10 letter groups in English language, like which ones are more frequently and such like, I guess nowadays, if you take a lot of sample text and use a computer and maybe machine learning or so, that would be something you can find out. But at the time of Shannon and those guys, this was not known. So the question is, how much does adding an order of approximation improve your ability to compress text? And here you see, according to the estimation that this guy Briouat produces, all letters equally probable, the kind of entropy is, no, I forgot what the definition of F is. Is it whether it's the entropy or the redundancy? Okay, the Fs denote the information in terms of bits per letter. Okay. If all letters are equally probable, 27 letters where we include the space, that makes 4.76 bits per letter, according to this concept of Shannon entropy that I'm going to explain later. If you include that certain letters are more common than others, that reduces the amount of information per letter to 4 bits per letter. And then 2 letters and 3 letters, you know, the number goes down. But, you know, as you take the limit of n goes to infinity, to what's the limiting value? Like, where does this converge? And this is not easy to estimate. He gives some estimate, basically, that F limit is unknown, he says. I'm talking about this part. F limit is unknown since very few data exist, on letter complexes of more than 3 letters. Okay, I suppose that might be different nowadays. For clue to the value of F limit, we can look to another set of statistics, that of the frequency of occurrence of words. That's similar to this Shannon idea that I showed you. These have been compiled both for use in coding and also for efficiency in learning a new language. Okay, blah, blah, blah. I'm not going to give you all the details. And with some smart estimation, he finds 11.82 bits per word. If you assume that the average English word, including blanks, contains 4.5 letters, we obtain as a limiting value estimated 2.14 bits per letter in the English language. That's not okay. That's not quite the limiting value, because there are still additional constraints that he hasn't taken into context. Shannon's estimate was, and I'm not sure where he said that, maybe it's later. Anyway, Shannon's estimate was that about 50% of the English language is redundant. And he actually, let me use this, because crossword puzzles are so popular apparently. He comes back to the topic of crossword puzzles, and he says that the existence of large crossword puzzles wouldn't be possible if the redundancy wasn't about 50%. That's his argument. And likewise, if the redundancy of a language is 33%, then you would be able to build arbitrarily large 3-dimensional crossword puzzles, according to his argument. So, well, but that's the rough estimations. Well, I hope that answers the question. Let's find my lecture again and go on. So this is the language story. So let's try to formalize this in a somewhat mathematical way. Yes. Okay, so the idea of Shannon was to model an information source as a stochastic process, a so-called Markov process. I'm not going to go into the details of this. Essentially, the frequency with which certain symbols or groups of symbols appear in messages follow certain statistical rules. They may depend on each other. The letters may not be independent. And those statistical rules have to be in such a way nice that average can be defined nicely. That's related to a property called algodicity, where if you take infinitely long messages, the relative likelihood of letters occurring in those messages in the limit of infinitely long messages should go to the likelihood that these letters have in the language as a whole. So there shouldn't be like a lot of infinitely long messages in which E is the least probable letter, if in the language as a whole E is the most likely letter. That's just important for defining averages in a nice way. And now the question is, how can we quantify the amount of information produced by such an information source? And again, let's look at a few examples. First, suppose you have a source that just, you know, where the key is stuck, where you just get 1, 1, 1, 1, 1 forever. A source which transmits one symbol endlessly conveys 0 information, essentially. The second example is a source where, let's say, either 0 or 1 is transmitted, and each time it's about 50% probability. A source which transmits 2 symbols with equal probability in the average definition for infinitely long sequences, each symbol being independent of the previous one and all the other ones conveys 1 bit of information per symbol. That, 1 bit is 0 or 1, so to say. Example 3 is kind of the intermediate case. Suppose we have a source which transmits 2 symbols with unequal average probability. So the 1 here is more likely than the 0. That's similar to how it is in the English language, where E is more probable than X. So clearly that kind of source has to transmit less than 1 bit of information per symbol, but more than 0 bits, which was example 1. And okay, coming back to the English language, due to redundancies and statistical correlations, sources which transmit in English language conveys less information per symbol than a source making use of order letters and signs in English language with equal probability. So English would be similar to example 3, and when all symbols are equally probable, that would be similar to example 2, which was the 0th order approximation to the English language that Shannon defined. But in general, what kind of measure for this information content can we define? So suppose we have individual events EI from a set of n possible events, and each happens with a probability pi. Of course, the probabilities have to sum to 1. What kind of axioms or nice properties could we wish for a quantity that defines the information content of such a process? We define a function that we call h. It's dependent on all the probabilities pi. Remember, they have to sum to 1. And the following properties should be plausible to you. First of all, h is continuous in all the probabilities pi. That's just nice to have mathematically. Example 1 above, remember this one, we argued such a source doesn't transmit information. So if one of the probabilities is 1 and all the others are 0, so that you have one and the same event for sure every time you try this out, in that case, the information content should be 0. Now I'm bringing that up here as a plausible axiom, but this is actually not independent from the others. It's actually going to be implied by the 4th axiom below, as we will see, but one step after the other. And now example 2 above, when all the symbols appear with the same likelihood, for n symbols, that would be p is 1 over n, 1 over n, 1 over n. This quantity should be monotonously increasing if we increase n. That means if instead of bits, we transmit twits or like 26 symbols, the more possible outcomes there are, the more information is then contained in one outcome. So this, I hope, is also clear. And now axiom 4 is very important. It's going to be one of the most important ones in the derivation, but maybe it's harder to understand. So let's go through this very carefully. H should be well behaved under splitting and combining events. So here we have an example, and let me illustrate that example for you. Suppose you want to apply for a job. You send your application letter to the company or the university where you are applying. Let's say with a probability of in total 1/2, they are going to get your application letter and just throw it away because they have other qualified candidates. With a total probability of 1/3, they are going to get your letter. They're going to invite you for a job interview in person, and then you don't do well and they don't give you the job after the interview. And with a probability of 1/6, they get your letter, you are invited to the interview and you do well, and you actually get the job. Now, based on how I have phrased this story, you may want to divide this into like you might want to divide you may want to combine the last two events. So let's look at this. With a probability 1/2, they receive your letter and throw it away. That's the same as before. Now let's say with a total probability of 1/2, you are invited to the job interview. That's the combination of these two. But once you make it to the job interview, your remaining probability of getting the job, your remaining probability of not getting the job is 2/3. So the total probability of being invited to the interview and not getting the job is still 1/3. Sorry, maybe I said that wrong. The total probability of being invited and not getting the job is 1/3. The probability of not getting that job after having been invited is 2/3. I hope that's clear. Similarly, once you are invited to the interview, your total probability of getting that job is 1/3, so that giving that your probability of being invited is 1/2. The probability of being invited and getting the job is still 1/6 as it was before. Okay, so this is how we want to, in a sense, split and combine events. And this function h should be behaved well under that. So let's look at these formulas here. H here of 1/2, 1/3, 1/6 is the h that corresponds to this kind of decision tree. There's 3 possible events that we have defined with these probabilities, so we get this h. If we split it like this first, where we have 1/2 probability of this happening and 1/2 probability of being invited to the job interview, that's h of 1/2, 1/2. That's the probabilities. And then with a probability of 1/2, you progress further. So this is the prefactor 1/2 here. You progress further, and your additional decision tree is this, where with probability 2/3 you don't get the job and 1/3 you get the job. So that's these probabilities here. This is how we want to split and combine events, and this is how h should behave when doing so. And these axioms are actually enough to derive the form of h almost uniquely. And I'm going to show you the derivation here. The derivation that I'm showing you here is going to be the one precisely as it's given in the Shannon paper. I'm not sure whether it's the most elegant possible one. On your exercise sheet for next week, we are going to guide you through a different way of motivating the form of h and deriving it, which, you know, if you don't understand or don't like this one here, then the other one may be more helpful for you. It starts from a slightly different set of assumptions and it goes through a slightly different route. But let's do this derivation as Shannon would. Okay, let's look at the case where all the probabilities are equal, 1/n, 1/n, 1/n. And that function we call a of n. It's just one function of one variable n. Assumption for the whole splitting and so applies if you have a of s to the power m, that is m times a of s. And you know, if you just rename these variables, a of t to the power n is n times a to the a of t. That may look a bit complicated, but you know, you can go through some simple examples and work them out. H of 1/4, 1/4, 1/4, 1/4 equals 2 times h of 1/2, 1/2. Similarly, if you have 1/9, 9 is obviously 3 squared, so you have 2 times h of 1/3, 1/3, 1/3. That's just a property that follows directly from assumption 4. Now, suppose you fix t and s, and you choose n to be arbitrarily large, and you find an m such that this holds. T to the power n should be between s to the power m and s to the power m plus 1. And now what you do is on both sides you take the log. So you have m times log s, n times log t, m plus 1 times log s. And now you divide after that by n times log s. Then you get precisely this line here, n over n is less or equal than log t over log s is less or equal than m over n plus 1 over n. And remember, n, we suppose we can take it large, so n over n is like a small epsilon. So what this tells you is that log t over log s has to be very close to m over n. Okay, that's just a fact. Now let's use the monotonicity that we demand. That's essentially, yeah, okay, continuous, and it's monotonously increasing. That's this number 3 here. If you apply A to this inequality, monotonicity implies that likewise A of s to the power m is smaller or equal than A of t to the power n is smaller or equal than A of s to the power m plus 1. And this property that we derived here can now be applied to get m times A of s is less or equal than n times A of t is less or equal than m plus 1 times A of s. That's another inequality. Now we divide all of this by n times A of s, and we get this, which looks very similar to this. So again, we see the difference between A of t divided by A of s and m over n has to be arbitrarily small with the small epsilon. And that just means that if A of t over A of s is close to m over n, and log t over log s is close to m over n, close meaning the difference is less than this kind of epsilon, then it means that log of t divided by log of s minus A of t divided by A of s is also less than 2 epsilon. So these two expressions also have to be very close to each other, and that motivates or implies that the function A of t is some constant k times log t. So we have derived this logarithm, which is very important. But this was all for the equal probabilities here. So far we have A but not H. So let's go on. We have shown that this holds where the constant k has to be larger than 0 because we want to satisfy requirement 3. Essentially, we just want this to be positive and monotonously increasing. Yes, so it's increasing, and log of n increases with n when k is positive. And now we use the splitting property in order to extend this to cases where the probabilities are not equal. So suppose rational probabilities where each pi is some ni over the sum over all ni. Imagine, for example, the following. Suppose you wanna you have an unfair dice or whatever, and you do the experiment with it, seeing what number comes out 1,000 times. And then how do you derive the probability of getting each result? Well, you count how often that result shows up, and that result divided by the total number of tries that you did is going to approach the probability in the limit where you do a lot of experiments. So the same we do here. We assume that essentially we have 1 over n, 1 over n, 1 over n, but we group them together. So let's say one result appeared n1 times, another one appeared n2 times, and implicitly we assume that n is very large. So due to this splitting property, this can be split into h of p1, p2. That's the h function for non-equal probabilities defined this way. And then we have these remaining terms where each term shows up with its own probability pi. And here we have h of the remaining 1 over ni, 1 over ni times, so they sum up to 1. This we know because it's given by this equation here. This we know because it's given by this equation. Those ni are all the same. So we can solve this for h of p1, p2, and so on. And we very easily get this equation. So this is the final result, so to say. H of the individuals, p1, p2 is minus k times the sum over all I, pi times log pi. Obviously, the probabilities are between 0 and 1, so the log here is always negative. That's why we have the minus here. And that completes the derivation of Shannon entropy, which is precisely this function for the set of probabilities pi. And the positive constant, we didn't fix it in this derivation. It's not really that important because you can absorb it into the choice of the base of the logarithm, like whether you want to use base 2 or base e, the natural logarithm, or base 10. Essentially, that defines how you want to measure your amount of information you want to, if you want to measure it in bits or nuts for the natural logarithm, or digits in the case of base 10. Good. Are there any questions about that so far? I know, let me say again, I know this derivation is maybe a bit tedious if you see it the first time. It's very, in a sense, it's very combinatorial with all these arguments, which of course makes sense for someone like Shannon, who works with probability and combinatorics. I was wondering whether the derivation that you're going to do on the exercise sheet is a little bit more natural from the point of view of a high energy physicist, because there you are essentially supposed to derive an ODE, an ordinary differential equation, for this function a of n. And well, obviously ODEs and their solutions feel very natural to us, but the result is the same in the end. There are no questions, I guess. Yeah, well, I'll come to that a little bit later. Maybe I can skip a few slides ahead. Where did I say that? Yeah. So here, this is the formula for Shannon entropy, right? You have minus k times these probabilities, and k is a positive number. And obviously, from statistical mechanics, this Boltzmann-Gibbs kind of entropy, which is given by this suspiciously similar formula. Here you have minus kb, that's the Boltzmann constant, times the same kind of probabilities here with the natural logarithm. And the Boltzmann constant has this value of something energy over temperature, joule over Kelvin. And obviously these two equations are very similar, but they're not quite identical. And people have argued about this. Some like to be more strict and say, well, they are derived differently. They are derived in, strictly speaking, different regions of physics, one information theory, the other thermodynamics. So just because they look the same, they don't have to be the same. Others are more kind of willing to accept that this similarity has a meaning, right? And Shannon doesn't really talk about the connection with the physics, the thermodynamics in his paper. Briouat did that in his book a lot, and he made the case that this similarity essentially shows that information has to be considered as a physical thing. Now, first of all, you see this Shannon entropy and Boltzmann entropy. They have different units. This one is just a number, or I mean, you can say it's in bits or so. This one has units of energy over temperature. But in a sense, that's kind of a choice that we make in how we define temperature. Here it's measured in Kelvin. And when temperature was first measured, they defined a new unit for it. Nowadays, we essentially understand better that temperature is kind of a measure of heat energy, right? I mean, in a gas, the temperature is related to the average kinetic energy that a gas particle has. And that means if temperature was a thing that's discovered nowadays, people might not define the unit of Kelvin for it. They might just measure it in terms of energy. 1 second, someone is writing in the chat. Boltzmann is perhaps the most nonsensical quantity in physics. Well, I mean, I don't want to be so radical, but it's true that, for example, when we go to so-called natural units like Planck units, we set the Boltzmann constant to just a number, usually 1. But essentially, the idea is that measuring temperature and energy would be not that outlandish, and then the entropy, even in statistical mechanics, is indeed also unitless, just like Shannon entropy. So essentially, this means that there is an information theoretic interpretation of the entropy in statistical mechanics, and the idea is, according to Briand, that in statistical mechanics you deal with a macro state and a micro state. The macro state is, what you observe with a state of a gas or so, which is characterized by some very few numbers, the temperature, the pressure, and whatnot. And then there's a microstate that describes the position and motion of every single particle that makes up that gas. And the idea is that, in a sense, the entropy is a measure of the amount of information that we would need in order to describe precisely which microstate we are in, given only information about the macrostate. Okay? Now, so far we have only discussed this for like discrete systems. Of course, the gas, the position of a molecule is a continuous variable, so there might be a bit more complication there. Shannon also defines his entropy for continuous systems, so that's just a tedious generalization. And so essentially, the idea is here that we are allowed to view information as a physical thing, and that we are allowed to view entropy in a sense as a measure of information, or a measure of our lack of information that we would need in order to describe the microstate, not just the macro state. Well, that's to a certain degree, that's something that we assume here. I mean, we may have good reasons to assume that, but people may want to be more cautious. And in the course of this lecture, obviously, we're going to talk about black holes, which, as was shown by Bekenstein and Hawking and others, you might think they have entropy because they obey certain mathematical constraints and laws that seem to mirror the laws of thermodynamics. And again, some people say, well, if it walks like a duck and it quacks like a duck, then it's probably a duck. And if black holes act as if they had entropy, then they probably have entropy. Other people might be more skeptical and more cautious. For a lot of the discussions about the black hole information paradox and the holographic principle, essentially, it will be our working assumption that these three quantities here are indeed related, that entropy has an information theoretic interpretation, and that black hole entropy has an interpretation as a genuine entropy in the sense of information theory and statistics. So we are going to take black hole entropy as a sign that the true theory of quantum gravity is going to have certain microstates that make up that are going to be responsible for the entropy of a black hole that is only described in its macro state by Einstein-Hilbert gravity. Okay, so as I said, that's essentially going to be the basic working assumption for a lot of the things that we are going to do for the rest of the lecture. And it's going to lead to these kind of questions. Do black holes have microstates? Does a black hole store information about what fell into it in the past, and what happens to this information when the black hole evaporates due to Hawking radiation? Okay, does that answer the question? So let's return to where I was. I skipped ahead a little bit. We had this, yes. Okay. So let's look at our example again. That's example 3, where we have either 1 or 0 being transmitted to us with unequal probabilities. That's essentially the kind of data that is produced by an unfair coin that shows heads in this, let's say 1, with a probability p, and tails, let's say 0, with a probability 1 minus p, so they add to 1. And the Shannon entropy for this as a function of p is plotted here, where we set the constant k equals to 1, and we choose the logarithm as base 2, so we really measure information in bits. If p is either 0 or 1, that's the kind of situation where the outcome is certain, and as we say, this corresponds to zero information, zero entropy. This curve here is maximized if p equals 1/2. So that's example 2. In the case where the outcome is unpredictable, I mean, it's always unpredictable, but in the case where all the outcomes are equally likely, the entropy is maximized and it's precisely 1 bit of information per symbol. That's the maximum here. And for all the other cases, we are kind of in between, and we transmit less than 1 bit of information per symbol. Okay. This Shannon entropy has a number of very nice properties that are helpful in its interpretation as kind of this information content. Let's just quickly go through them. Setting k equals to 1, just to be sure. H is positive, and it's equal to 0 if and only if one of the p's is 1 and the other ones are 0. So I'm using the Kronecker delta here, but essentially what I mean is, if you have the one certain event and all other events are impossible, then this information is 0, as we saw in the plot on the previous slide. If all if you have a fixed number n of events, and all of them are equally likely, so that the probability is 1/n, that's the maximum that you can achieve for n number of events. That's what we also saw here. The maximum of the curve is precisely when all the 2 events that we have here in this case are equally likely. And the probability was 1/2. It's also symmetric under permutations. The order in which you give these arguments here doesn't really matter. Now there's one very nice property. Suppose you have independent events, EI, that happen with probability PI, and events Fj that happen with probability Qj. Like, let's say you're flipping 2 coins at the same time or whatever. The probability for joint event is, let's say, EI happens and Fj happens, that's P of Ij. And we assume those 2 events are independent, so the joint probability is just the product of the 2 probabilities. And that means that Pi, for example, is Pij if you sum over all j, because the sum of all Qj is 1. And similarly, Qj is the sum over I of the Pij, because the sum of the Pi over I is 1. So you can write down H for this set of probabilities for both events. That's this for Shannon entropy. And you can write it down for each of the individual events. Then you get these 2 formulas here, which you can spell out more complicated like this, using these properties here. And if you just add these 2, you see that for the independent events where this really holds, the H for the combined probabilities is just the sum of H for the one probabilities and the sum of the Q, and the H of the other probabilities. In general, these 2 events, the E's and the F's, don't have to be independent. And in that case, the H is smaller than the sum. And the interpretation of this is that the uncertainty of a joint event is never higher than the sum of the uncertainties of the 2 individual events, or the amount of information you get out of it. Good. So let's, yeah. What is this good for example, in the theory of, transmitting information? The entropy H plays a role in Shannon's theorem for a noiseless channel. And of course, Shannon famously generalized this for the noisy channels, which are very relevant in technological applications, but let's keep it simple for now. Okay, suppose you have an information source which produces signals with information content H bits per symbol, and a communication channel has a capacity of C bits per second. then it's possible to encode the output of the source such that you can transmit via that channel an average of, well, C/H symbols of the original message per second. Maybe a little bit less if there's like an epsilon that can be arbitrarily small. You cannot transmit more than that. You cannot transmit at an average rate of more than C/H, what is it, symbols per second. And okay, that's maybe a bit technical. I'm not going to give the proof of the theorem. Instead, let's look at a very nice example. Suppose we have a language, again, it's kind of a model of a language where all the symbols and letters are statistically independent, but they appear with different frequencies. You have 4 letters, A, B, C, D, and A appears with probability 1/2, B appears with probability 1/4, and the other 2 C, D appear with probability 1/8 and 1/8. So they sum to 1, that's good. And successive letters are independent. For example, a typical sentence or word in that language may look like this: C, A, B, A, 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 C, B, A, A, D, B. What's the entropy of this information source? Well, you can, oh, sorry, there's a bracket too much here, but apart from that, you can just calculate H of these probabilities. You know, you have 1/2 log of 2, 1/4 log of 4, twice 1/8 log of 8. You get 7/4. 7/4 bits per symbol compared to the optimal that you could achieve with a 4-letter alphabet, which would be 2 bits per symbol. So there's obviously a bit of redundancy here. It's not quite optimal for information transmission. So let's try to encode this. Remember the example that we had with the Morse code, where it's beneficial to assign a short symbol to a likely letter and a long kind of sequence to a rare letter. Let's try this out. So, okay, this is the language. This is our example sentence. Suppose we want to send the above sentence. Ignore this number here, sorry. Via a binary channel, which can only transmit 0 or 1. So we kind of have to figure out a way to transcribe a letter into like a sequence of zeros and ones. The naive encoding that we could use is simply this: A is 0, 0, B is 0, 1, C is 1, 0, D is 1, 1. That uses exactly 2 bits per symbol, because, you know, because obviously. That means we transmit on average 1/2 letter per second. 1 bit takes 1 second. 1 letter is going to take 2 seconds. So we transmit 1/2 letters per second. And if we encode this typical sentence or word in this way, we end up with this. 12 letters have been transcribed or encoded into 24 bits. Well, how can we do better? Let's try a different encoding, as I said, one which is kind of in spirit similar to this encoding that's done for Morse code. Let's do an encoding where A is 0, B is 1, 0, C is 1, 1, 0, and D is 1, 1, 1. So clearly the most likely letter is given the shortest sequence, and the least likely letters are given the longest sequence. You can do it as an exercise if you want. If you transcribe this message via that encoding given here, you end up with this sequence which has 21 bits. So it's shorter than the 24 bits with the naive encoding. So let's do the numbers for a second. The original message contained 12 letters with average H 7/4 bits of information each. Hence, the total information was about 21 bits. And using an efficient encoding, we were able to actually achieve that and transmit that sentence in precisely 21 bits. So we found an encoding in which the channel can transmit up to C/H. That's 4/7 letters per second. And that's obviously more optimal than the naive encoding on the previous slide. So this is, in a sense, this is how you know, compression algorithms work. And there's a funny thing here. This is optimized based on the statistical properties of the kind of toy language that we have defined. You could construct a sentence, let's say, which is just DDDDDD or CCCDDD. That letter, according to the statistical, or that sentence, according to the statistical properties of this language, would be very, very unlikely. But maybe, well, you could still construct it. And then this kind of encoding would actually produce an encoding which is longer than the naive encoding. So what you see here is that this encoding is optimal for the typical message of that language. It's optimal for the average message. There's always, if you want to compress data, there's always a case of input data where the compression algorithm would expand the data. That's kind of a general feature of such things. Actually, when thinking about the exercises, I thought whether it would be a funny exercise to give you to say, figure out or write, either by hand or by some kind of algorithm, a text file that increases in size under trying to compress it with zip or so. But well, I didn't put it on the exercise sheet because I thought that might be a bit outlandish. But in principle, such a file should exist. Are there any questions about this so far? No, you have to think about it. Wait, where's the theorem here? You have to think about it like this. So suppose h was 0, then this would explode, right? The ratio here. Because we want to transmit, this is about how many symbols of the original message we can transmit over the channel on average, where we also assume kind of a limit of large, long sequences. So suppose example 1, the sequence is just 1, 1, 1, 1, 1, 1, 1. Essentially, I can transmit the message. Listen, this message is just once forever. That's a finite message that I transmit via my channel, and it describes all the infinitely or arbitrarily large sequences that this language produces. So this is kind of effectively the most efficient conceivable compression algorithm, where I give a descriptor for an arbitrarily long message which is finite. And so that makes sense that for the case where h goes to 0, this kind of average rate actually diverges. I hope that answers the question. Are there any other questions? Good. So let's go on. Yeah, here we already were. This we already said. Okay. Yeah. Okay. I already explained this as an answer to the question earlier on. Essentially, our fundamental assumption from now on is going to be that these two equations here are not equivalent by coincidence. There's a meaning to that, namely that entropy has information theoretic interpretation, and that's also going to lead us to this all the paradoxes surrounding black hole entropy, and whether that has to be interpreted as from an information theoretic point of view, and whether certain paradoxes arise from that. Are there any questions about this short segment? Okay, I guess not. Good. So let's finish off the lecture with another very, very important and fundamental paper on information theory and the physicalness of information, namely the famous paper by Rolf Landauer, which leads to Landauer's principle, in case you are familiar with it already. So this is from '61. Landauer analyzed a simple model of information storage in a computational device. Because if you have a computer, sure, you may want to think about your data from a point of view of information theory, but that data somewhere has to be stored in a physical manner. It has to be stored in like magnetic particles or whatever, and that's physics. So you have to be able to apply physics to the computation process. That's Landauer's argument. And he analyzed a simple model of how information might actually be stored in a physical system. For that, he considered that in a computer, suppose you want to store 1 bit of information. How would you do that in a like toy model that's easy to work with? Suppose you have a kind of a energy potential landscape like the one here in this figure, which has 2 distinct minima. And a particle might move around in that potential. There's 2 minima of energy. One we call the 0 state, the other one we call the 1 state. And you can now store, in a sense, information by putting a particle with the minimal energy either in the 0 position or in the 1 position. And that corresponds to the logical bit that is stored on your computer, we assume. And now Shannon wanted to know what happens if I delete information? What happens if I want to erase information? And for that, he considers specifically irreversible computational processes, where a computational device is considered logically irreversible if the output state does not uniquely determine the input state. Essentially, that means that you can do a computation and results from intermediate computations can be deleted once they are not needed anymore. And it means that, for example, before a certain computation step is carried out, maybe you want to reset a certain bit to a specified initial value. Like suppose you have an algorithm where you need an initial bit, which is 1. And you don't know or you don't care what the result of the previous calculation was that was done on that bit. So for your purposes, that bit might be either in the state 0 or 1. And his argument was that this kind of process necessitates dissipation. So consider this potential well example for 1-bit memory. And now you don't know whether your particle is in the states 1 or in the state 0, but you want to make sure that it ends up in 1 by applying some time-dependent force to it in addition to the force that generates this potential well. What kind of force could you use such that the particle ends up in the state 1, no matter whether it was in the state 0 or 1 to begin? Well, that's not quite possible, as you can argue by looking at the time reversal process. In the time reversal process, you have a particle that starts in 1, and then you apply the force f of minus t or minus f of minus t or so to make that process go in the other way. And then it would have to end up in either 1 or 0. So from one initial condition, you would have to end up in 2 different end conditions with the same likelihood, and that's not quite possible in a like time reversible process. But if there's dissipation in the system so that the particle can lose energy, then the argument with reversing time doesn't make sense, or it doesn't apply. And it's indeed possible to find a time-dependent force, f of t, that makes sure your particle ends up in state 1, no matter whether it started in state 0 or 1. So this is very important because Landauer's principle explicitly only applies to irreversible computational processes. And that is a good approximation for most computers in the real world. However, from a theoretical point of view, I think people are seriously looking at whether like architectures would be possible with so-called reversible computational processes. But let's look at this case that Landauer defined. So you need dissipation. That means a particle is going to lose energy, and that also means that you're going to create, in a sense, waste heat on the environment. You're going to increase the entropy of the environment via this dissipative process. Dissipation just means kind of friction and things like that. I hope that's clear. So let's go through this. suppose you have a bit which might either be in 0 or 1. So there's one bit of information stored in your computational process, and you want to restore it to the state 1 via a dissipative process. As said, we go from a situation with 2 possible states of equal likelihood, in Shannon's terms h equals 1, to a situation with only one allowed state. In Shannon's case, that's h equals 0 for that bit or for that system. That means that in a sense the information decreases by delta h of equals 1. You literally delete one bit of information from your computer memory, but because this process is dissipative, you can show that the statistical entropy of the memory device would decrease by an amount of delta S. That's the statistical physical entropy now. KB, the Boltzmann constant, equals natural logarithm of 2. So the point is that by deleting this bit, not only the information entropy seems to decrease by 1, also the statistical entropy. And of course, by the second law of thermodynamics, we would think that we can locally decrease the entropy if in the environment it increases as a consequence. So the irreversible erasure of one bit necessitates the environment to gain at least that amount of entropy. And that corresponds to an entropy increase, an energy increase or an increase in the waste heat by the environment which we use as heat bath via the first law of thermodynamics by at least this amount of energy, which is dependent on the temperature of the environment. And this is Landauer's principle, that this should be in an irreversible computer the minimum amount of energy that gets lost when erasing one bit of information. This is actually, well, obviously a very interesting kind of conclusion. People have argued about this for ages from the point of view of science, philosophy, and what the implication of that is for the relation between information theory and physics. People have tried to measure it experimentally. They claim with success. So you can look at this paper if you like. It's also been discussed whether this kind of fundamental limit is going to pose a restriction on the energy consumption of computers. Real-world computers are far away from that limit so far, but I mean, depending on who you ask, it's projected that we might get to the state where this kind of fundamental limit might become relevant for computers in the real world within like a decade or two. So this might be very relevant, and probably that's also a reason why people might be interested in these more reversible machine kind of configurations for computers. Are there any questions about this so far? Well, that's the end of the lecture for today. So I hope you all stay healthy, and I hope you all come back next week. And of course, take a look at the exercise sheet. Are there any questions for the lecture as a whole anymore? Everything is clear? Well, in that case, I thank you all for your attention and participation. I hope to see you all again next week, and I hope you stay healthy.